Hi, Astronomy. Mr. Janowski here. This is part 8 of the chapters 14 and 15 slides. In the last two parts, we talked about the corpses of low mass stars and then the corpses of the lower mass, high mass stars. So, low mass stars are stars up to about 8 solar masses. Low mass, high mass stars, the lower mass, high mass stars, are between about 8 solar masses up to about 20 solar masses. And then in this part, we're going to talk about the corpses of the higher high mass stars. So stars that have a mass when they're alive of between of 20 solar masses or more. So the corpses of these stars, it turns out, are going to be really, really bizarre and really interesting stuff. So let's get started with this. So, what is the upper mass limit of a white dwarf? The Chandrasekhar limit, 1.4 times the mass of the sun. So, this means the star itself, when it was alive, had up to about 8 times the mass of the sun, but its core, after the outer layers drift away in the planetary nebula, its core has to be about 1.4 times the mass of the sun or less. So, second question, what is it that prevents gravity from crushing a white dwarf? It is electron degeneracy pressure. So, this weird quantum mechanical effect that means electrons don't like to be too close to each other, which I know sounds like the regular old electromagnetic repulsion. They're like charges, but it's actually different. It's a quantum mechanics thing. So, next question, what's the upper mass limit of a neutron star? About 3 times the mass of the sun. So, the living star that left this was it was between about 8 and 20 solar masses, but its core is going to be between 1.4 and 3 times the mass of the sun. And what is it that prevents gravity from crushing a neutron star? It is neutron degeneracy pressure. So electron degeneracy pressure is not enough, but then at a certain point, neutron degeneracy pressure kicks in, and this supports gravity and keeps it from crushing the star. So if you remember, a white dwarf ends up being about the size of the Earth, basically, of an ordinary planet. A neutron star is going to be the size of a city, so it's more massive, but it's crushed down even more because electron degeneracy pressure wasn't enough. And now we're going to get to the last kind of corpse. So, just a quick review. Low mass stars up to about 8 solar masses, their core is going to be up to about 1.4 solar masses. And gravity's trying to crush it, but electron degeneracy pressure is enough to defeat gravity in that case. And you end up with a white dwarf. If your living star was between about 8 and 20 solar masses, that means the core of that star is going to be between about 1.4 and 3 solar masses. And electron degeneracy pressure is not enough to support that one, but neutron degeneracy pressure is. So that's what holds these stars up, and that leaves you with, the very bizarre and interesting neutron stars. So if your living star had a mass of more than 20 times the mass of the sun, its core that it leaves behind after its supernova, type 2, stellar collapse supernova, is going to be 3 times the mass of the sun or more. So what is strong enough to counteract gravity in this case? Turns out nothing is. Nothing is strong enough to counteract gravity. Gravity's going to win. Gravity's going to crush this thing all the way down. And this is going to leave us with a black hole. So, low mass star gives you a white dwarf. A lower mass, high mass star is going to leave you with not a neutron star, a neutron star. And the higher mass, high mass stars, its corpse is going to be a black hole. Not shown to scale here. It should actually be much smaller. We'll get to that in a second. So I'll put a link to this. This is the Crash Course Astronomy video on black holes. So interesting stuff. Here is an artist's illustration of a black hole, and here is an actual image of a black hole. This is M87 star, the supermassive black hole in the center of the galaxy M87. So, talking about black holes, escape velocity. So we had this earlier in the year. This is the minimum speed needed to escape an object's gravitational influence. So, for example, the escape velocity from the surface of the Earth is about 11 kilometers a second. So, if you leave the surface of the Earth flying straight away at 11, I think it's 11.2 kilometers per second, you're going to have escape velocity, which means you won't ever come back down. You're just going to coast away forever. And when you're infinitely far away from the Earth, you'll still be barely moving away from the Earth. So, yeah, that's what escape velocity is. This was way back, I don't know, chapter 4, chapter 3, something like that, when we first started dealing with this. So here's our formula for escape velocity. If we're looking at this, big G is this gravitational constant. M is the mass of the thing being escaped from. So not the mass of the rocket or whatever, it's the mass of the planet we're trying to leave. And R is the radius of the planet, the distance from the center of the planet or star out to its surface. So if we're looking at this formula, 2 and G aren't going to change because 2 is a number and G is a constant, so those don't change. If the mass of the object gets bigger, well, it's in the numerator. That means escape velocity is going to go up. And if we look at R, if R gets smaller, it's in the denominator. That is also going to make escape velocity go up. So when we're dealing with the core of a very massive star, it's going to have a whole lot of mass squeezed into a very tiny radius, which means we're going to have a very big escape velocity. So if you take this formula and rearrange it and solve for R, and then for V escape, you plug in this special number. You plug in C, which is the speed of light, 3 times 10 to the 8th meters per second. So 300 million meters per second. So start here, do the algebra, solve this expression for R, and then replace V escape squared with C squared, and you get a number called the Schwarzschild radius. I know it looks like Schwarzschild, but it is actually pronounced Schwarzschild. And this is the radius to which you must squeeze a body of mass m down in order to cause it to be a black hole. So the Schwarzschild radius also defines the event horizon of a black hole. So here I took this formula, and this first case, this is about the smallest black hole you're going to get from a star collapsing. So the smallest core that can collapse to form the mass of a black hole this way is about 3 times the mass of the sun. So I started with this formula, and then for m I plugged in right here 3 times, and this is the mass of the sun. And if you do all this, you end up with 8,840 meters. So a little bit less than 9 kilometers is the radius of this thing. So these things are going to be even smaller. A small black hole is going to be even smaller than a neutron star. And this is about as small of a black hole as you can get. Now, the sun is not going to end up being a black hole, but you can still calculate the Schwarzschild radius you would need to make this thing. So this time I just plugged in the mass of the sun, and I get an even smaller one. So only about 3 kilometers across. Now, the Earth is far less massive than the sun, and the Earth certainly is not going to be a black hole. But it turns out if you plug the mass of the Earth into this formula, you end up with 8.84 times 10 to the minus third meters, 8.84 millimeters, basically. So a little bit less than 1 centimeter. So if you squeezed the entire mass of the Earth down into something that's basically the size of a marble, you would have a marble-sized black hole. So there's not actually a way to do that, but if you could, that's what you would have. Now, that just gives you an idea of how extremely dense a black hole is. So think of taking the entire Earth, everything that's on the Earth, every mountain, everything in the mantle and the core and all that stuff, crush all that down to the size of a marble, then you have a marble-sized black hole. That's how dense these things are. And just for fun, you can take a bowling ball with its mass. So this is about 7.26 kilograms. I think that's about a 16-pound bowling ball. You'd have to crush it down to this way super microscopic size in order to have a black hole with the mass of a bowling ball. So that's how the formula for Schwarzschild radius works. So the smallest black hole you can get from this process, this is the collapse of a dead star. So we would call this a stellar mass black hole because the mass of this thing is only about 3 times the mass of the sun. So the smallest black hole you can get is about 9 kilometers in radius. There are other types of black holes. The center of pretty much every galaxy We now actually think that it's every galaxy has a supermassive black hole at its core. So these can be millions or even billions of times the mass of the sun. And we're not sure how these things form because it doesn't seem like there would be enough time for smaller black holes to just keep colliding to form these things. But we know they're there. We've seen one. We have an image of one. So yeah, these things can be much bigger. So M87 star, this is the black hole in that famous picture from the Event Horizon Telescope that came out last year. This one has a radius of about, what are we looking at? About 18 billion kilometers. So this thing is huge. So the smallest black hole you're going to get is about 9 kilometers in radius. This one has a radius of about 18 billion kilometers. So about 120 astronomical units. So this particular supermassive black hole is about the size of the solar system, which is crazy. But an ordinary black hole, just from the death of a star, is about the size of a town. It's slightly smaller than a neutron star. It's the distance from here to like Easton. Yeah, it's pretty tiny. So black hole anatomy. At the center of the black hole, you have what is called the singularity. So this tiny little point here, perhaps of infinitesimal volume, so a true mathematical point. It gets complicated. We're not going to go that far into it. But this might actually be a point of zero volume, and this is where all of the mass is. So nothing was able to keep gravity from crushing this thing all the way down, as far as we can tell. So yeah, all of the mass of the black hole is here. And then if you go out one Schwarzschild radius, which that's going to depend on the mass of the particular black hole you're looking at, if you got one Schwarzschild radius in every direction, so think of this radius as kind of defining the volume around this black hole. So what is in this volume? Essentially nothing as far as we can tell. So all of the mass is here, and all of this volume out around the singularity, there's no mass there. There's nothing there. But that is basically the volume of the black hole. But space and time, it gets so bizarre, it's even problematic to talk about volume of a black hole. And so what would be the skin of the black hole? So the skin, the surface of this black hole, all the points that are one Schwarzschild radius away from the singularity, that is called the event horizon. And why is it called that? It gets weird. So yeah, here's this idea that your singularity, this may be a point of zero volume. We know of nothing. Gravity is trying to crush all this stuff together, and there's so much mass, and gravity is so strong at this point. We know of nothing that can keep gravity from just crushing everything literally all the way down to zero volume. So you might end up with a point of infinite density, or not. It gets weird. Maybe string theory kicks in at this point and keeps this from happening. No one's really sure. Our models of the universe, the physics we have for this stuff, don't really deal with this situation very well. So anyhow, if you've taken chemistry, you might remember the formula for density. So the density of something is mass divided by the volume. Well, in this case, we have a mass of about 3 times the mass of the sun divided by zero volume. So now we're doing what you're not allowed to do in math. We're dividing by zero. So what is the density of this? It's undefined. It's kind of infinity. It's weird. Yeah, all this stuff is just very weird. So anyhow, you have this big volume. Well, big, relative to a city, small astronomically, with about 9 times the radius. About 9 kilometers in radius. And there's nothing here in this whole volume. And all of this mass, 3 times the mass of the sun, is all squeezed down into this tiny point of perhaps zero volume. Very weird. So what's going to happen if you fall into a black hole? So if you've had Physics 1, you'll remember this, and we did talk about this at the start of Physics 2 at the beginning of the year when we were doing general relativity. You would experience these very strong tidal forces. So what are tidal forces? Anytime there's a difference in the gravitational pull on one side of a body compared to the other, we call that a tidal force. And this is literally what leads to the tides on Earth. So if you stand up on the surface of the Earth, you're experiencing a tidal force, but a very, very tiny one, because your feet are very slightly closer to the center of the Earth than your head is. So look at the formula up here at the top left. So the distance to your feet is a little bit smaller than the distance to your head. And because the distance is in the denominator, that means the force of gravity at your feet is a little bit stronger than the force of gravity at your head. So gravity's pulling on your feet slightly stronger than it is pulling on your head. But the difference in force is so slight that you can't even measure it if you're standing on the surface of the Earth, because the Earth, as massive as it is nothing compared to a black hole. If you start falling towards a black hole, so let's assume like this astronaut, you're falling in feet first, what's going to happen? Well, if your feet are closer to this enormous mass of the black hole than your head is, you're going to get these tidal forces. And because you have so much mass, once you start to get close enough to this black hole, the difference between the force of gravity at your feet than at your head starts to be really, really big. And eventually it would start to stretch you out. And the technical name for this is literally spaghettification. So these are the extreme tidal forces you get when you get too close to a stellar mass black hole. And you would get stretched out, and eventually, the molecular bonds between, all of your cells aren't strong enough to hold them together. So you get ripped into a long, hot string of soup pointing in towards the black hole. So in my opinion, it should be soupification, but the technical term is actually spaghettification. So, yeah, not vegetarian soup. This would be kind of beefy tasting and all red. Yeah, it's gross. Yeah, human soup, not good. So I'll put a link to this video too. Describes this thing, spaghettification, as you fall into a black hole feet first. Now, interestingly, and a little bit counterintuitively, you would get spaghettified for sure if you fall into a smaller mass black hole. So this is a black hole with maybe 3 times the mass of the sun, 10 times the mass of the sun, 20 times the mass of the sun, but a fairly small one. So anyhow, the idea here is in this graphic. So here I have the singularity, is this point. It should be a point of 0 volume, but you can't draw that. So there's your singularity. This surface is the event horizon of the black hole, and the red dashed line is kind of the spaghettification zone. So this is where, if you're falling into this black hole, if you get this close, at this point you're getting spaghettified, you're going to be ripped apart, you're going to be killed at this point. So you can't actually be alive when you fall into this kind of black hole. Now, the thing that is counterintuitive is if you had a more massive black hole. So if we're talking about one of these supermassive black holes at the center of our galaxy, the Milky Way, or the center of M87, which is another galaxy, you actually can get to the surface of this black hole. So why is that? So the thing that's dangerous, the thing that actually spaghettifies you, is when you get too close to the mass of the black hole, which is all at the singularity. So the singularity is really the dangerous thing. So if you look at this supermassive black hole, notice its spaghettification zone, it's bigger than this spaghettification zone. It's further away from the singularity of this supermassive black hole. However, the event horizon is even further away still. So what that means is if you had one of these big, I mean literally supermassive black holes, if you were falling into this one, you could actually cross the event horizon before you got so close that you get spaghettified. So you could actually literally fall into this black hole and be alive while it happened. And if the black hole were supermassive enough, it might not even feel weird. It gets complicated. What would you experience? What would you see? At least in this case, we don't know of anything that would kill you at this point when you get to the event horizon. So maybe you actually could fall into this supermassive black hole. And then, just a naive explanation of this is, you get close enough to the singularity if you keep falling, if that's even what happens. At a certain point, you do get spaghettified and you get ripped apart. So I don't recommend trying this because at some point you're going to get ripped apart, either before you even get to the black hole, if it's just a stellar mass black hole, or shortly after crossing the event horizon, if it's a supermassive black hole. So, to review, what prevents gravity from crushing a white dwarf? Electron degeneracy pressure. What prevents gravity from crushing a neutron star? Because electron degeneracy pressure is not enough to prevent gravity from crushing a neutron star, but neutron degeneracy pressure is. So what prevents gravity from crushing a black hole? Trick question. Nothing. Nothing prevents gravity from crushing everything in the black hole all the way down. In this situation, gravity wins. So the kind of stellar corpse compact star you end up with is based upon what is strong enough to defeat gravity. So in one case, electron degeneracy pressure, that'll give you a white dwarf. If it's a more massive star, a more massive core of the star, this won't be enough, but neutron degeneracy pressure will, and you end up with a neutron star. If the core of your dead star is even more massive than that, then even this won't stop it. And turns out there's nothing that is strong enough to stop gravity from crushing you all the way down, literally to an infinitely small singularity. And in that case, gravity wins and you get a black hole. So, what point is at the center of the black hole where all of the mass is contained? This is called the singularity. So, what is the name for the distance from the singularity out to the surface of the black hole? And that distance defines kind of the volume of the black hole. That is the Schwarzschild radius. And here's your formula for Schwarzschild radius. I said Schwarzschild radius. And finally, the last thing. What is the name for the surface of the black hole? That is the event horizon. So yeah, here's your basic black hole anatomy. As bizarre as the physics of these things is, the actual anatomy of a black hole is really, really simple. You have all of the mass at the singularity, and then you have nothing for one Schwarzschild radius out to the surface of the black hole, and then you have the event horizon. So, yeah, that's what it is. And that's how a black hole do. For the next part of the slides, we'll talk more about black holes and get a little bit weirder with this stuff. But yeah, hopefully you're finding this interesting.